Good morning. The sun has risen on another day at the CogX research stage. Sadly, my curtains remain closed to maintain consistent lighting levels for you throughout the day. Don't forget that you can tweet using the hashtags TuringCogX and CogX2020 if you want to share your thoughts on any of the content that the Alan Turing Institute has curated for you today. At this point, I would normally introduce your moderator for the session, but you're stuck with me today. So I'm Will Taylor. I'm Research Project Manager for Urban Analytics at the Alan Turing Institute. And I'm delighted to be moderating this morning's session, which is about data-centric engineering and the built environment. We've got a great lineup of 4 speakers for you this morning and a panel session. At least 3 of them will be talking about various types of digital twin, but we'll also be going on an excursion through Zen first. So our first speaker is Professor Sally Cripps. Sally is an internationally recognized scholar and professor in Bayesian statistics. She's a professor of maths and statistics at the University of Sydney. She's also the director of the Centre for Translational Data Science. And Sally is going to talk to us today about Zen and the art of Bayesian geology. So, Sally, over to you.
Thanks very much, Will. Good morning, everybody. I'm speaking from Australia, so it's evening over here, so it's dark. I'm going to talk today about Zen and the art of Bayesian geology. I'm going to hopefully ask Will to start playing my slides. Will, have they started?
I believe so. Can you see them?
I can't see them, but if they're up, that's fine. I'll just talk. Okay, so and I'll say next when I want the next one. As Will said, I run a data science centre, which is essentially about quantifying uncertainty in natural resources, and the goal being to quantify the risk inherent in making decisions regarding the stewardship of Australia's natural resources, to ensure that Australia has a economically viable but also an environmental. So when we first started doing this, we started just exploring geology. It was Zen and the art of Bayesian geology. But as we've gone along, we've realised that it's not just geology that we're interested in, but also hydrology and ecology. And Bayesian framework is obviously a natural approach for addressing onto, should we allow mining? It brings up the question of what does that do to the groundwater and what does that do to ecology? And so we have to all take them into a sort of much larger framework, and that's what this work is all about. So that's the explanation for why geology, hydrology and biodiversity, but why do I say we need to be Zen? It's the reason I say that we need to be Zen is because these problems present some of the hardest data science projects that I've ever worked on. They involve working at the interface of the data science, domain sciences industry, and quantifying uncertainty in the natural resources is incredibly difficult. As you can see, hopefully, by the posterior distribution in front of you, I apologise if some of you don't understand the term posterior distribution. Hopefully, if you don't, you will by the end of the talk. So basically, the quantifying uncertainty via posterior distribution is what we do. And if you look at that posterior distribution in front of you, it's a very difficult object to quantify and explore. So that's why I say we need to be Zen. So if you could move to the next slide. So natural resources are small data complex model problems. And that is what makes them so challenging. The distribution of the outcomes in natural resources problems, so for example, sinking a mine or deciding whether or not to lock up a national park, it has very high varied outcomes. It's very difficult also to reverse some of those decisions. You can't reverse the decision to drill a borehole because it's, well, at least you can, but it's very difficult. The data in these issues, these are small data problems, they are few and far between, and Bayesian methods offer a principled approach to fusing various sources of the uncertainty from various sources of information, quantifying uncertainty at every stage of the process. Next. Essentially, all the problems that we work on are complex model problems. They are inversion problems in the sense that for a given set of outcomes, we have very many explanations. And given that that's the problem, then constraining the model space or constraining the number of possible explanations is key to getting to finding out or getting solutions to these problems. So we use Bayesian reasoning, like a lot of people at the Turing Institute would do, and to perform not just what I call data fusion, but information fusion. So we are going to fuse information not only just from data, but also from what we know about the physics of the problem. When you're working in a lot of the geology problems, the hydrology problems, where there are hardly any data, you rely very much on the domain science to inform you in some way about likely outcomes, or at least to restrict the space. That's actually key to a lot of these problems. This is not a problem. These are not, although we have lots of data, we have hardly any data on the actual problem of interest. These are small data problems in the sense that we hardly ever observe what we actually want to observe. Okay, the posteriors are incredibly difficult to explore, as I've already talked about. Methods for exploring them that require gradients, such as HMC, are clearly not going to work because the gradients don't exist in many places. Variational inference is rubbish because it can't cope with distributions that look like that. So what a lot of our work is to come up with new techniques to find and try and quantify uncertainty by effectively exploring that posterior. Next. I'm hoping we're looking at a page that has Bayes' theorem on it. So basically, just to recap what I just said is, we work very closely with the domain scientists to actually come up with novel likelihood functions that incorporate the physics, that incorporate their expert opinion or previous work via prior distribution. And, obviously we turn the handle and we get that posterior distribution. So I'm going to talk about two specific types of worlds that we're going to explore in this talk. A world is characterized by this Greek letter theta. The theta represents the thing I don't know and I want to find out about it. Next. Okay, so I'm just going to talk about a couple of worlds that we want to find out about. The first one is I do want to know about what exists under Australia up to 5 kilometres below the surface. One of the reasons I might want to do that is because I want to locate granite intrusions that are very much below the surface because I'm interested, for example, in geothermal energy. And there's such a place called the Cooper Basin in South Australia where people did just that. They were interested in finding out, actually mapping the entire structure of what was underneath the basin in order to inform decision makers about where the most likely places for granite were. It's got to be clear here that there are hardly any observations underneath the surface at that depth. So it's not like we have a lot of data on the problem that we want. We have a lot of surface data. We have a lot of sensor data. We have magnetic, we have seismic, we have gravity sensors. We have more data at the top than you really know what to do with, but it's still a small data problem because all of that is not actually observations on the quantity of interest. And I'll talk about how we use that sensor information in the next couple of slides. So that's one example. So actually, trying to figure out what lies 5 kilometres below the crust of Australia is a very similar problem to trying to find out what the landscape looked, in this particular case in New Zealand, 25 million years ago. And we wanted to do that because we wanted to actually try and find out about paleoclimate, about rainfall as it existed, 25 million years ago, or what it was then and how it's changed over time by looking at how the landform changes. And so in this particular problem, we're going to be bringing in physical models which are to do with tectonic plate movements, which are to do with the way that rainfall erodes certain rocks, what the qualities of the rocks are, and we're going to do this in order to get a picture of what the climate looked like for the last 25 years. So, as the slide says, small data problems, very little interest of data on the quantity of interest. Next. Okay, so how do we use this data together with all the sensing data to try and find out about, for example, what lives below the Earth's crust? On the left-hand side, you've got a sort of a cartoon of what might it look like underneath Australia? The grey bits are granite intrusions, the other coloured bits are different coloured rocks. And here a world is going to be characterised by a unknown number and type of different type of rock structures which are similar. So we want to actually recover a partition of the underground where the partition is over different types of rock structures. So we propose a world. I'm not going to go into detail here because we don't have enough time of how we do that. But let's say we propose a world, this theta, and that theta represents what that structure looks like and what the rocks in each part of that structure are. Then what we do is we say, well, if that world is the real world, then we use all the physics, the forward models, whether those forward models are gravity or magnetic or seismic, to say that if that was the real world, would I be likely to observe at the surface? We compare it to what we do observe at the surface using likelihood functions and various types of likelihood functions, and then we accept or reject those draws with the usual metropolis ratio. Now and that's essentially how it all works. So it's just a proposing, and obviously the way you propose the worlds is key, and I'll come to that because that's actually the hard part. Another hard part is because there's no analytic solution to the forward models of shapes such as you're seeing on your screen. So we actually have to divide that world up into little cubes, we have to voxelize it in order to compute what we would expect to see on the screen. And this itself gives some of those horrible shapes that you saw. So there's lots of rich areas for doing data science and MCMC type of algorithms in this space. Next. Okay, and next. So here you should be looking at a slide that has a dragon on it. Of course, if the posterior distribution looked like the distribution on your left, it would be very easy, but unfortunately it doesn't. So if we could move slides to the two next, which you'll see, once you get real data, then we start getting distributions that look like what you see on the left there, with which are discontinuous, they're irregular. Sometimes those discontinuities are to do with the physical constraints, sometimes they are to do with just the voxelization that I talked about, but they're the things of interest and we want to try and explore them. Next. How do we, so this is where we go to how do we make a difference in the sort of the data science literature. What we do a lot in the centre is actually work on real problems with a view to actually developing new data science techniques that are inspired by those problems. So here we've been working on problems to do with the natural environment that industry is very interested in, for example, particularly with the mining and the geology, but also a lot of governments are interested in climate and what impact that is. So by starting off looking at that, we now then start to realise just how difficult these problems are, and we come up with proposing new data science techniques. And so this one is not a new one, we're getting to the new ones, but initially, how do you possibly explore those posterior distributions? Well, it's never going to be one chain is enough. So parallel tempering is a bit of a no-brainer in terms of what you want to do. However, then you're still stuck with how do you move within a particular chain, what sort of proposal distributions, how do you explore that space? And what this slide shows is that, one way is a random walk. The next panel down is if we use a Crank-Nicholson, and the third one down is adaptive random walk. And what you're seeing here is trace plots for the density of the rock that we identified as layer 3. Now, you'll notice that all these proposal distributions, none of them are HMC, none of them are things that require gradients, because we actually, for two reasons. Firstly, it's really hard to get gradients even if they existed, and secondly, a lot of the time they don't exist. So that's the challenge, is how do you do that? As you can see here, the Crank-Nicholson proposal works well, but the adaptive random walk appears to be doing well, but we're still not sure really whether this distribution of density is bimodal, which the adaptive random walk would seem to suggest, or whether it's unimodal. So different sampling schemes will give you different results. Next. There's the posterior probability of granite at a depth of 3.5 kilometres below the Earth's crust for different runs. Ideally, we would like to see them all the same to convince ourselves that they've converged, and largely they are. But the idea here is that we're not actually pinpointing or saying there is that's where granite lies. We're saying actually this is the posterior probability of the granite. So this is the probability of it, so that they understand the uncertainty attached with any estimates that they're going to use in order to know where to drill. Next. This is another one. We did this same thing. Now we're not in the Cooper Basin. We wanted to look at the probability of finding a type of mineralogy in the Gascoyne in Western Australia. That was to work with a mining company. They were interested in finding out a certain mineralogies in a part of WA. Next.
Sally, if you can try and wrap up in the next couple of minutes, that would be useful.
I've got 30 seconds I've got on my clock, so
Right.
I've been talking a mile a minute. Okay,
Yep.
So the last set of results is here. We've got, and I haven't shown you here the uncertainties, but we've got uncertainties around this too. This is what the evolution of the landscape looked like. So 25 or 250 in that case, 1,000 years ago, that's what the landscape looked like and how it's eroded over time. And these themselves gave rise to our estimates of rainfall. And what it was 25 million years ago, which was that original slide you saw. So by understanding how the landscape has changed over time, this is what we've been able to show. So what does it mean to be Zen? Well, it means to be Bayesian for a start, to use all available information in a principled way. So we're not just adding ad hoc bits in and out. We're actually, in a logically consistent fashion, fusing all sources of information to get proper uncertainty quantification over the objects of interest. Next. Future directions. I'm just going to quickly run through these. One of them is to, incorporate models that have lots of faults, which is what we're working on at the moment. So modelling faults underneath is quite tricky. Next. Next again, I'll pass that. Okay, I'll talk to this one. So we're coming up with new proposal densities that actually adjust to the local geometry of the distribution. However, the caveat there is that the derivatives exist, and of course, a lot of the time they don't. So the latest piece of work we're doing, which is pretty exciting, is we've actually adapted the effectively Hamiltonian Monte Carlo to be able to incorporate discontinuities. And what you're seeing in front of you there, down at the bottom, is a set of slides which show a distribution that has boundaries that look a bit like butterfly wings and a triangle. And the panel B is the algorithm that we're working on. And you can see it recovers those boundaries much more effectively than something like a NUTS or a baseline HMC. So that's where the research is going. And next, thank you very much.
So thank you very much, Sally. Great talk. I particularly liked that picture of the Zazen frog in the top left. Next up, we've got Professor Michael Batty. Mike is the Bartlett Professor of Planning at University College London. He's also chair of the Centre for Advanced Spatial Analysis. He's a published and successful author, and most importantly, from my perspective, he has a digital twin project with the Alan Turing Institute, which I think he'll mention today. So Mike is going to talk to us today about simulating urban futures.
Thanks very much, and apologies to everybody in the audience that somehow it's supposed to be a kind of seamless presentation, etc. But Will is showing the PDF basically. If any of you want to actually download this PDF, then if you go to my Twitter account and J Michael Batty, all one word, J Michael Batty, then you can actually download it. I've actually downloaded it to my phone at the moment, essentially. So we have several versions of it, but of course the version we should have had isn't quite there. Okay, so let me kick off. Simulating urban futures. And if you could put the next slide on, Will, that's basically where you can get it from. Sorry, the previous slide to that is location. Okay, you can't read that directly, but next slide. This tells you a little bit about what I'm going to talk about. I'm going to talk about cities and their futures, and in particular, I'm going to talk about the idea of high frequency and low frequency cities. That cities which are high frequency are things that we look at in cities over the next 2 minutes or 5 hours or whatever. Low frequency cities are when we look at cities over much longer periods of time, over years and decades. And the two examples that I'll show later on, which are digital twins, and I'll define that, of course, in a moment, really relate to these different sorts of cities. So I'm really going to talk about where the digital twins come from. Of course, they're models in some sense, and the big conundrum is how close is the digital twin to the real thing. I'll talk a little bit about maps as analogies. Maps basically are kind of twins in a sense. We use them to look at the real world in this context. And then I'll talk about many different types of models, many different types of digital twins. And last but not least, I'll give you my two examples, the high frequency city, which is all about modeling transit basically here in London, and the low frequency city, which is really all about modeling cities right across the UK. And finally, I'll finish up by trying to evaluate this. And I hope that the presentation will accord with what follows, because I think the next two presentations will in fact be, again, aspects of digital twin. Next slide, please, Will. Okay, so high frequency and low frequency cities. I've sort of defined this to some extent by saying that the high frequency city is all about what happens over, if you like, the next 24 hours in the city. And of course, the high frequency cities have become much more significant in the last 10 years, in the last 20 years or so, as computers have become embedded into cities and are producing big data in real-time streaming. If you go back 20 or 30 years, when people looked at cities, they tended to look at the low frequency city in this context. So to some extent, computers and the whole digital revolution has actually changed our conception about what aspects of cities we look at. We look at many more aspects today. Next slide, please, Will. Okay, so where do digital twins come from? Well, to some extent, of course, digital twins are models, etc. And of course, I don't need to tell this audience that a model is an abstraction, it's a simplification. We tend to throw away more things in a model than actually keep. So to some extent, the best models are the simplest in that sense. So the best models are where we throw away most things and we actually keep the essence, basically, in that sense. So how can we actually think of the model as a twin in this sense? Because twins seem to be far too close to the real thing that we're actually representing. And so all this talk is really all about how close we can actually get to the real thing in this particular context. So of some senses, the digital twin, basically, as opposed to a physical twin in some sense, the digital twin is largely because many of the systems that we're simulating are in essence becoming digital, if not digital already. Next slide, please, Will. Okay, so in other words, let me make 4 points about digital twins. First, the models depend on the media. If the media is close to the real thing in some sense, if the real thing is the media in that sense, then to some extent we are talking about the idea of a digital twin. So digital media to some extent is really all important. The second point is the digital twin can also be used for predicting the future, basically, to some extent. But models can actually be built about the future, not about the present. And in that sense, are we talking about a digital twin? The third point is the digital twin is reactive rather than predictive to some extent. To some extent, if we're predicting something that doesn't exist in some senses as yet. And in that sense, can we talk about a digital twin? And fourth, digital twins are all about a coupling, a relationship between the original and the model itself, a transfer of information. It might even be thought of a digital twin as a kind of a controller. So these are all aspects of digital twins. Next slide, please, Will. Okay, so where do digital twins come from? In fact, Go back about 20 years. Apparently, a chap called Michael Greaves in production engineering was one of the first people to talk about digital twins in that sense. And of course, in production engineering, then you can begin to think of models, basically, which are very close to the system itself. Now, let me digress very slightly and talk a little bit about digital twins as maps in some sense. There are some excellent examples. I'm going to tell you a little story here from Lewis Carroll, which he wrote about in his last book, basically in 1893. It's a conversation between a German gentleman and me, myself, in that sense, or the author, basically. So if you move on to the next slide, Will. The next slide actually shows the conversation. I'm going to read this out very quickly. So I begin by saying what a useful thing a pocket map is. It's all about a map in this context. So the Mynheer, the German gentleman, says, that's another thing we've learned from your nation, said Mynheer, map making, and we've carried it much further than you. Would you consider that the target map to be really useful? Yes, about 6 inches to the mile would be the scale. Only 6 inches, exclaimed Mynheer. Very soon we got to 6 yards to the mile. Then we tried 100 yards to the mile, and then we came to the grandest idea of all. We actually made a map of the country on the scale of a mile to a mile. Have you used it much? I inquired. It's never been spread out yet, said Mynheer. The farmer's objective, they said that it would cover the whole country and shut out the sunlight. So we now use the country itself as its own map, and I assure you it does nearly as well. Now, there are many people who've actually talked about maps in this particular context. How close can you get to the real thing in that sense? Next slide, please, Will. Next slide, thanks. And there are Luis Borges in a wonderful essay on exactitude in science really talks about this particular idea. And let me just finish my digression about digital twins by showing you a couple of pictures, if you like, perceptions of maps in this sense. So next slide shows the famous picture from the New Yorker. Next slide, please, Will. And also a later thing from, this is how a New Yorker sees the world. And then on the right, how China sees the world in this particular context. Okay, next slide, please. Multiple, I'm going to miss the next two slides basically because I think that we're running a bit short of time here. The next is, let me turn to my examples. I've got two examples here which I'm going to race through very quickly, very impressionistic basically. First of all, the notion of building a model which is actually close to the real thing. This is a transport system. It's a transport model. It talks about vehicles and passengers and so on. It's essentially a model of our tube system here in London, basically. And of course, that's become almost entirely digital in terms of how passengers actually interact with it. Most people on the tube system are having to use a smart card now to pay. In some senses, much of the information in the tube is digital in that context. And at the same time, we also have a situation where we're talking about the trains in some sense providing information. So next slide, please, Will. Okay, so that's our typical simulation model. It's real-time simulation. We have demand by travelers. You can see on the left there, that's a picture of the so-called Oyster card, basically, but you can pay by credit card, etc. in a sense. And the kind of data that comes from that is really quite important. Transport for London don't really use that data as yet. It's only used for payment purposes, basically, but they are beginning to think how they can actually link it, which is the demand by travelers, of course, to the supply of trains in that sense. So on the other side of things, the supply of trains, basically, where they are on the network and so on, is all organized digitally. So we have two databases here in some sense, putting them together, and they're actually close to real time in some sense. There is, in fact, a major issue here that demand and supply can't really be connected. If you get into the tube system and start walking around and trying to get onto a train, basically, then for a whole range of reasons, your movements are not tracked. And there are various bylaws that relate to confidentiality and so on. So the real issue in the sense is how can we actually model demand and supply basically in this particular context? How close is the model? Because the supply of trains is almost in real time, basically, that it's used for the TrackerNet system is used to actually look at trains in that sense. So this is a classic example of how close can we get. Now, the next slides actually show a little bit of data on this. Next slide, please, Will. The next slide that shows basically the rail network. Basically, think of that network. The world I live in is in terms of networks. Think of that network. Think of every other network in the city that relates to it. That's just the rail system. The bus system, of course, uses the same thing. The Oyster card in that context. And then there are many other networks that really interact with that. So that's a measure of complexity. Next slide, please, Will.
Mike, we are running a bit short of time, so I'm going to have to ask you to ruthlessly prioritize the rest of the content.
Okay, so let's just click those slides on one after the other. The next one, I'll tell you. Okay, that's okay. These are all examples that you can download yourself and see. Basically, let me move on to the next example. Quickly move those through. Basically, they're all aspects of this, and I'll talk about the last example. This one, the quant model. The next slide, please. So these are the long-term change models, basically. Very different, in fact, from what we've just looked at in this context. We're talking about long-term change here. We're talking about the next slide, please, Will. The next slide will show pictures. Basically, we have a system that basically is looking at infrastructure projects over the next 10, 20, 30 years in some sense. And that's a model, a digital twin, which is very different, much more abstract in a sense. Now, I'm going to finish at that particular point. You can download the PDF from Anne J. Michael Batty, go to my website, etc., and download it in that sense. And really, I suppose, to finish it all off, we're really talking about how close is the digital twin, how close is the model really to the real thing. And of course, as we got more and more into the digital world, basically, the models are getting closer and closer to the real thing. And of course, ultimately, they merge with the real thing. But of course, that's the great conundrum. Can they actually merge with the real thing? Probably not. So I'll stop at that point.
All right. Moving swiftly on. Our next speaker is Dr. Myriam Neaimeh. Myriam is a group leader in the data-centric engineering program at the Turing. Her team's working on the technical and social aspects of vehicle grid integration, developing digital twinning tools for electricity distribution networks, and assessing cybersecurity threats to the EV ecosystem. She's going to talk to us today about digital twinning of electricity distribution networks to support the uptake of low carbon technologies. And we also want to hear the audience's thoughts on digital twins. So if that first poll hasn't dropped already, can we drop it, Louis? Over to you, Myriam.
The energy sector is starting to embrace the power of data. Historically in the UK and in most other places, energy datasets have been fragmented and siloed. In addition, there is a lack of good quality data, but crucially, there is a lack of experience in the energy sector to deal with these large datasets. At the Turing, we are working with automotive and energy companies to develop a cloud-based tool to help automate the collection and analysis of large datasets coming from new forms of energy demand, such as electric vehicles and energy supply sources. We are also developing methods to understand the impact of these sources on the energy system to help with electricity network planning. I mentioned electricity network planning. This slide is showing the physical subsystem of the electric power system. So we are seeing here the generation. So you have your large power plants, the transmission system in blue, and the distribution system in green. We are focusing on one component, the electricity distribution networks. These are the physical wires and electrical components that are needed to transport electricity from the generation sources to our houses, buildings, and factories. Now, there is an ongoing change taking place and impacting the whole system, but specifically, the electricity distribution network is facing a new era. We have more distributed energy sources connecting to this network, and we have new uncertainty coming from new forms of demand, such as electric vehicles. And electric vehicles can help us transition to both a decarbonized transport and power system. In the transport system, we could move to driving from using fossil fuels to using renewable energy. So this is how electric vehicles can help decarbonize transport. In power, electric vehicles have big batteries that can help support the operation of the power system by, for example, taking surplus renewable energy and using this energy later on where the system is in stress. But charging those electric vehicles is significant. And we have targets to move to all new cars and vans to be effectively zero emission by 2035. And a large portion of these cars would be battery electric. So what would be the impact on the power system? Charging an electric vehicle is like plugging a whole new house. So we need to manage the demand of these cars to ensure that our electricity network can cope. And key to this is to manage the charging demand. And to allow us to manage the charging demand, we need controllable chargers. So these chargers can allow you to control the rate, so how much you charge, the time, when and how much you let the car charge, and also the direction. So you can charge the car, but also you can discharge the car. And the last bit, controlling the direction, is quite a new and novel charging technology called vehicle-to-grid. And we are testing it as part of a large demonstration project called E4Future. And we're working closely with automotive and energy industries, such as Nissan, who's the project lead. And now the aim is to help understand how we can operate these electric vehicles to help the operation of the electricity network, put in more renewable energy while taking into account the user needs. Taking into account the user need is key. So to meet these needs, we need to understand how is the system functioning. So we need a lot of data, and we need data coming from cars, we need data coming from the chargers, and we need data coming from the networks. So we have a lot of data coming from new sources, and we need to deal with it. And now our challenge is to automate the collection and analysis of this data. The last thing we wanted on this project is that several project partners sending us several data sets over email and Excel files at different times. So we wanted to avoid that. So we wanted to automate this process, but we also wanted to ensure that we are securely storing, sharing, and analyzing this data. And most importantly, we wanted to make the most of this data. So how to use and analyze the data to get insights on the operation of the network to help figure the planning of this network. Possibly, this can enable network companies to upgrade the infrastructure where it is needed the most. Because any upgrade, if it is deemed necessary to maintain the reliability of the supply, is ultimately paid by us, the customer, through our energy bill. So it is best to target investment in the right places to minimize the cost of upgrades. And we need tools to help us find these right places. And that's why we're creating such tools to help with this. I have to say, we started this project just to automate data collection to make our work easier, but we want to ensure continuity. We want to ensure what we spend time and resources building can be used beyond this project. And that's why we wanted to get this cloud-based platform tool up and running. And it could be used not just to collect and automate data collection and analysis, but can be used to run network planning studies. We are in beta version now. We can access the tool through a secure web browser. And then accessing the tool looks something like this. What we're seeing now is a part of the tool where we can ingress data from electric vehicles as smart meters, and run a distribution and run a probabilistic method to get a probabilistic distribution of the demand. And then after that, we use that as an input to the simulation of the networks. So we build the distribution model of our electricity networks, and then we simulate these networks and we test what's happening on the networks when we add electric vehicles. And what we see on the right is voltage and the loading of the transformer. So in the same way that we want to check if a person is doing well, we check their temperature. For the electricity networks, some of the metrics we use to check if everything is running okay is the voltage and the loading of the transformers. And so we're creating those digital twins, so computer models of those electricity networks to help us simulate what happens, for example, like what Mike just said, if we want to predict the future, what happens if we have a lot of electric vehicles? What happens if there's a lot of electric vehicles with photovoltaics? What happens with these networks? And we are using open source tools on this platform. So as long as a tool to, for example, OpenDSS, help us model and simulate this network is open source, we can include it in this cloud-based platform. And this is the first example we have here. This is the Nissan Technical Center in Cranfield, where we installed the first 20 chargers. So we build a digital twin, a network model of the actual electricity network. So now we have a computer model to tell us what can happen on this network if we add electric vehicles, if we add photovoltaics, and we would use it in our studies. So again, why are we doing this? Why are we building this cloud-based tool? Why are we doing a digital twin of the electricity network? We want to expand the toolbox of the network planner. Electricity, this electricity distribution network industry is a risk-averse sector. And their planning tools can take years in testing before they come operational. So we wanted to create a tool that the planners can use in addition to their business as usual tools, an agile tool to carry bespoke studies on part of the networks that seem problematic, using new sources of data, not estimated, not historic profiles. And also we wanted to make sure that we can do power flows more often than what usually happens, which is typically maybe once a week. And now power flow is what allows us to check the metric, the health of the network. So it gets us the results of voltage and capacity of transformers, as an example. Oh, okay, so it hasn't been necessary so far to carry those power flows to check the state of the network often. But in the inclusion of new technologies like EVs, new changes of the network, it becomes necessary to do this more often. It becomes necessary to check different parts of the network and don't assume that all networks are homogeneous and they will all behave the same. And that's why we needed such tools. Because of this certain...
Apologies to rush you. We are running behind time still, so if you could wrap up in 2 minutes, that would be really helpful.
Thank you. So this digital twin will help us make better decisions. What we're doing is we're creating pipes to these new data sources. We're unlocking data to better query it. So we're not just looking at one data type, we're looking at the combination of data. And then we're using state-of-the-art systems. So there has been a lot of advances in the last couple of years. So why wait for years for a tool to be tested? Why not have an agile tool to make the most of the cloud-based systems, to make the most of the latest data science tools? And we're taking into account privacy-preserving techniques. I will skip this slide on another aspect of modernizing energy data. And here it's talking about the importance of communication standards. I will not go into detail. I'll just say that right now, those different companies involved in the electric vehicle charging, they're developing their own languages to speak with the different components in the system. And this will lead to a fragmented infrastructure. So we're making here a point that we need those companies, we need those entities, different components to speak very few languages. So we have to go towards very few common standards. And these standards need to be secure, because if you have people entrusting the internet to charge and discharge their car, they need to trust that their data is going to be safe, and they're going to have to trust also that the battery is going to be empty when they need it, and not a hacker comes into the system and discharges the car or sends wrong pricing information, as an example. And this is why these communication protocols need to be secure. If you wanted to learn more about communication protocols, about cybersecurity, then we are running a smart charging webinar that you can find. If you just search for smart charging webinar, you'll find the link for the previous slides, for the YouTube playlist, and for the upcoming episodes. And we have 3 upcoming episodes on cybersecurity specifically. For everything else I mentioned, you can check our website at the Alan Turing for information on this project and other work. Thank you.
Thank you very much, Myriam. Another great talk. Our final speaker for this session is Dr. Themistoklis Botsas. Themis got his PhD at Durham. He's now a research associate in the data-centric engineering program at the Turing, where his research focuses on multi-phase flow systems. And he's going to talk to us today about digital twinning for engineering, design, and control. So over to you, Themis.
Thank you very much, Will. So I'm going to continue also about the talks regarding digital twins, but this time in the context of multi-phase flow systems. So those are systems that essentially are dealing with problems of fluid flow of more than one phases, which is a region within which the material is uniform or approximately uniform in terms of physical properties. So let me see if we can start our presentation. Okay, hopefully you can all see this now. So I'm going to start with an overview of digital twins. So in this slide, I have a couple of definitions from IBM and Siemens, the combination of which kind of give us a big picture of what digital twins are all about. So they're essentially virtual representations of some sort of physical systems, which, and in our context, this is very important, are using real-time data in order to help us better understand, learn, and even make predictions and decisions about the performance and the characteristics of the system. So let's see some differences between standard traditional models and how we're going to approach them with digital twins. So we start with a multi-phase flow system. We have some sort of method to collect data from that, with which we are going to build some sort of model. From the output of that model, the user takes some action, intervenes with the system, and maybe changes its operational modes. This is going to lead to a new set of data, a new model from scratch, and this circle goes on and on. On the contrary, when it comes to the digital twins, we start once more from the multi-phase flow system, but this time we can possibly have some sort of automatic data collection technique, which is going to build our model. And then we can even have some sort of autonomous decision-making without the user intervention, which is going to change the mode of the flow system. And this is going to lead to a new set of data, which is going to update the digital twin. And now we've got this sort of pipeline. So in order to better understand the problems dealing with the digital twin, we have some sort of metrics and the different levels among those metrics. So starting with the autonomy, this is effectively the ability of a system to take action without human input. In the lowest level, we need human input in all sections of the system, of the problem. When we go to a bit of a higher level, the system can have some sort of autonomy, but it's user-assisted. And in the top level, we have complete absence of human intervention. Next, we've got the intelligence, which is the ability of a system to replicate human cognitive process. In the lowest level, again, the system has no intelligence. Then at higher levels, it then start reacting to stimuli or maybe use some historical data in order to make more educated decisions. And at the top level, it reaches self-awareness. Then we go to learning, which is the ability of the system to learn from the data without explicit programming. In the lowest level, everything has to be hard-coded. In higher levels, it can use supervised learning, even higher unsupervised learning. And at the top level, it can use reinforcement learning, so effectively interact with the environment on its own. Finally, we've got fidelity, which is related to the level of detail of the system. So effectively, it's associated with some sort of degree of calculations or measurements, and whether they approach the true value or at the very least the desired standard. At the lowest level, we have conceptual problems and models, and at the highest level, we can go for a high degree of accuracy, and which is pretty important because we need to take some critical operational decisions. So why go to combine the concept of digital twins with the multi-phase flow problems now? Where there are a few reasons. First of all, the huge impact that the computational power has in the past few years. This is pretty important in our context, mainly through the shift in focus on cloud simulations, which we're going to talk a little bit later about. Then we've got new types of sensors that can deploy data faster and reduce measurement uncertainty. Interesting visualization techniques like augmented reality and virtual reality, and also many advances in machine learning in terms of different frameworks, algorithms, and models that people can use. For example, if we like to couple this concept of real-time data, we have new, very interesting sequential techniques that can be very nicely done. So what sort of impact can we expect? First of all, in terms of value, we obviously expect to save some cost, and this is directly related with all the other points on that list. Remembering the autonomy that I mentioned, we have some absence of human intervention, so this will cause reduction in the required workforce. Directly related to the intelligence is the flexibility, since now the model can on its own choose between different operational modes. And again, having the idea of the real-time data updating our models, this is directly going to have a huge impact when it comes to our efficiency and mainly in our safety. Now, how are we going to deal with this? There are three main components that we need to combine. The first one is the physics, in our case, in general, the domain expertise. The second has to do with the statistics, machine learning, and AI. And the final one is everything cloud-related, like computing and storage, and also the data streaming component. So in the next section, I'm going to talk a little bit more about those, what each of those brings to the table when it comes to digital twins, what happens if we only use two and not the third one, and finally, in what mode each of those couples is related. So starting with the physics, those provide us, of course, with differential and partial differential equations, which can give us some insights about the underlying processes that construct the models that we're dealing with, and also are pretty important for prior knowledge and maybe sets of rules in a rule-based system, which is not only going to exclude non-physical results from our cases, but also help us decrease by a significant amount the space in which our algorithms and our models need to work. Next, we've got statistics and machine learning, which provide us with probabilistic frameworks and principal ways to quantify uncertainty, for example, through a Bayesian model. But also, it gives us new algorithms, model, and machine learning techniques, which we need to keep in mind, though, that not all of those are going to be interesting and useful in our case. There are some limitations, especially if we need to use the real-time streaming component. Finally, we've got the data streaming and the cloud storage, which obviously is going to provide us with a way to have storage, to store our data into databases, and then use queries in order to extract them and use them for our models, which again are going to also be built on the cloud. Next, we go to pairs limitations. What happens if we take off the node of the data streaming? Obviously, we lose this real-time data update, and this is going to also cause a delay in the critical decision-making. And we also are going to see some issues when it comes to storage and computations, since now we might have to have access to some access and a lot of storage. If we take off the statistics and machine learning node, we might still be able to see some results by solving directly the analytically the differential equations, but this is going to be very slow. It's going to have an effect on computational time and also need for high resources. By the end, when we do get a result, the system might have already been involved, so a result won't be useful. Finally, if we only use statistical machine learning and the data streaming, we don't get the expertise, so we might get poor performance and maybe even some non-physical results. So the physics and the statistics and machine learning combined are going to provide us with fast, interesting surrogate models that are also going to include the expertise through maybe some prior or a rule-based system. The physics are going to be combined with the data streaming through IoT Internet of Things sensors that are going to immediately, from the source, stream the data into the cloud. Finally, the data streaming and the statistics component provide us with online or incremental learning methods that then can be nicely coupled with specific machine learning techniques, like, for example, ensemble Kalman filters or some forms of reinforcement learning. So I'm going to finish my presentation with a couple of concept applications. Let me just say first that for all those applications, we do have the individual pieces, and we're kind of in the process of integrating them into some sort of pipelines. So the first one has to do with monitoring and maintenance for flow-induced erosion. In this figure, you can see a pipe where the black dots denote particles of sand, and when they hit the walls, they induce erosion. So the idea here is to start by having some IoT pressure sensors on the walls, which are going to immediately stream data to a cloud database. And within this, within the cloud, we can create some sort of surrogate model. For example, maybe some Gaussian process model. This is going to be informed by either a set of rules or a prior distribution from the experts. And using it, we can, the idea is to help the engineers visualize it with augmented and virtual reality. For example, seeing a 3D replica of this pipe and seeing in real time how the pressure changes and whether that causes some trouble. Through the output of this surrogate model, we can also make some predictions and take necessary actions. For example, whether some sort of components need to change. And this, of course, is going to feed in the pipeline with a new different set of data. And this is going to be a continuous process. The other application has to do with safety critical prediction of reactor entrainment and emergency cooling performance. So here you can see a reactor where liquid is flowing down the walls. If the reactor reaches a very high temperature, that triggers an emergency procedure. So it needs to be cooled with some sort of stream of air and water. Once more, we're going to start by collecting data with sensors. This time it's going to be mainly temperature data, and deploy them in some way to a cloud database. We can now construct within the cloud a decision model using probably a Bayesian framework in this case, since the uncertainty is pretty important and crucial for this sort of problems. So we're also going to inform this with an informative prior. And then here's where the autonomy comes in. The digital twin is going to decide whether to take or not action. If it does, then it is going to trigger that emergency cooling, which is going to lead us to collecting more data. If it doesn't, it just keeps on business as usual. So no matter what, we still keep collecting real-time data. And that, of course, is a continuous process, whether we do trigger the emergency cooling or not.
And
so,
this,
yep.
The usual 2-minute warning. Sorry to interrupt. Just wrap up in the next. Oh,
yep. So that was it. My presentation is done. Thank you very much for your attention. Let me just give shout out to the open access data new data centric engineering channel. You can follow them and see them in those links. And yeah, thank you very much for your attention.
Well, thank you for a great talk, Themistoklis, and thank you for surprising me by keeping to time and making my 2-minute warning redundant. I hope everyone enjoyed that session. For those of you with the correct pass, there will be a Q&A session with the speakers starting in just under 15 minutes time at 11:15. For those of you who don't have that pass, The next session will be starting at 12 in the same place, and that's on data science for science. So I hope to see most of you back there at 12. Bye for now.
Want access to more CogX videos? Subscribe now for free at cogx.co.